All right, introduction to vectors. First of all, what is a vector? Many physical quantities, such as speed, can be completely described by a single real number called a scalar. Scalar. This number indicates the magnitude or size. A vector has both magnitude and direction, so there's a difference. A scalar is simply a number describing something like speed. But when you add direction, then it is called a vector. So direction matters with vector, all right? So think about football, yardage, okay? You could say the number of yards, but if you don't tell if it's a gain or a loss, it doesn't really matter. That's a vector, okay? Because it is a direction. You can't just say, oh, they got 15 yards. 15 yards, or they lost 15 yards. If you just say 15 yards, you need to tell them if it's a gain or a loss. There is direction and it matters, okay? And so when you introduce not just distance, but also direction, then you have introduced a vector, all right? And they're represented by something that hopefully will be familiar when we get to it, the little arrows, but that's why we have the arrowheads on them to tell direction. All right, let's talk about types, just identifying between the two. It says, state whether each quantity described is a vector or a scalar. A boat traveling at 15 miles an hour. It's scalar. There is no direction. A hiker walking 25 paces due west. That's a vector. A person's weight on a bathroom scale. Scalar. Hence the term scalar. All right. And so they've given you some more examples here. You'll notice the differences. Like 1A, we have the word east of south. That gives you direction. A parachute falling straight down. That gives you direction. A child pulling a sled with a force of 40 newtons. There is no direction there. Okay, so just identifying the difference between a scalar and a vector. All right, let's look at some terms here, some terms. A vector can be represented geometrically by a directed line, also called a ray, right? We have an initial point here, and a terminal point here. You'll notice that it has a tail and a head tip or a tip of it. The notation for a vector looks very much like a ray, but you'll notice that it just has one end of your little arrowhead on it. So your notation for a ray is either the two capital letters, starting point and ending point, initial point and terminal point. Order matters when you list it because you have told me the order of it when you list it. With a little half arrow, it can be with the lowercase if it is notated with a lowercase, and then you'll also notice that it is bold without notation at all. That also indicates a vector, all right? A vector is initial point, origin is in standard position. The direction of the vector is the directed angle between the vector and the horizontal line that can be used to represent the positive axis. The direction is 35 degrees. So here's the deal. This is standard position. Standard position is very much like you would represent it on a coordinate plane with unit circle. It is from the x-axis and it is counterclockwise. That's standard position. Magnitude, when they say magnitude, they are talking about the length of the segment. And they have done this in a scale factor, which is actually how they teach the problems. And I actually teach the problems from a unit circle perspective. But if the scale of the arrow is 1 centimeter for 5 feet, then the magnitude denoted absolute value of the bold A is 2.6 times 5 or 13 feet per second. And so they've taken the length and given you what the actual length would be not in scaled form, all right? So magnitude represents length. Direction is represented typically by degrees, all right? There's two other ways that we talk about direction. Look at the top of page 483. Direction of a vector can also be given as a quadrant bearing, or phi, which is the Greek letter that they've given you there. It's a directional measure between 0 and 90 degrees east or west of the north-south line. The quadrant bearing of vector v shows 35 degrees, and that's on the other one, by the way, the one we just saw. So on this one, they're talking about this one, here we go. The quadrant bearing of vector v is shown 35 degrees east of south. East of south. Okay, so when you hear these words in a word problem, east of south. So if we picture this, north, south, east, and west, okay? East of south is here, okay? East of south is here, west of south. And you also have to pay attention to how they are describing it in a word problem, because they may say they are walking south east, that's one direction, or if they say they're walking west of south, like it just have to pay attention to how they're saying it in the terminology. All right. So if they're walking south and they go east of that, well, if they're walking that way and go east of how they're walking versus true east. So you have to pay attention when they're saying it, what they're actually telling you. True bearing, you're going to see this as well. Directional measurement where the angle is measured clockwise from north. So true bearing, standard position starts here and goes counterclockwise. Quadrant bearing, they give you direction. So they will say some direction between 0 and 90 degrees, and they'll tell you southeast, southwest. They'll actually tell you the direction. And then we have what's called a true bearing. This starts at north and goes clockwise. So this 145 would be a true bearing. It is always given using 3 digits. So even if they gave you something like 25, it would say 025. And that tells you that's a true bearing starting at north and 25 degrees clockwise from north. Okay. And so you have to pay attention to how they've given it to you and what these types mean. So it says, use a ruler and protractor, draw an arrow diagram for each quantity described, include a scale on the diagram, 20 feet per second at a bearing of 30 degrees. So you'll notice that they gave you the bearing 030. That is a true bearing. That means from north, we're going to go clockwise 30 degrees. So from north clockwise, a true bearing. When they're talking about direction and they don't give you north, south, east, and west, you're going to assume a true bearing here when it's 3 digits. And so the way that I would actually note this is I would actually put 20 feet per second. I would actually write that here on my vector itself, right? I would actually label that as my 20, which is probably what y'all did in physics, I would imagine. I don't know that y'all did it on a scale factor. 75 pounds of force at 140 degrees to the horizontal. That's standard position. When it is to the horizontal, these words right here, they're going to indicate that you start at the horizontal and go counterclockwise to the horizontal. So that's where we get the 140 degrees. 30 miles per hour at a bearing of southwest 60 degrees. All right, southwest 60 degrees. And so we're going south and west 60 degrees. All right, and then of course 30 miles per hour. All right, parallel vectors have the same or opposite direction, but not necessarily the same magnitude or length. The marks are the same. Those parallel marks are something we've used all the way since geometry. Vector A, B, C, E, and F are all parallel. It does not matter that they are facing different directions, and it does not matter that they are different lengths. We're talking about just parallel. Do they have the same slope from the horizontal? Equivalent vectors have the same magnitude and the same direction. In the figure, A equals C because they have the same magnitude and direction. Notice that A does not equal B. They're parallel, but they're not the same length. A does not equal D. They're the same length, but they are not going the same direction. So they have to have both direction and length to be the same, magnitude and direction being the same to be equivalent. Opposite vectors have the same magnitude, but opposite direction. The vector opposite A is written negative A, which makes sense. In the figure, E equals negative A. They have the same magnitude, but they are going different directions. So same length, different directions. Those are opposite vectors. Think of it from geometry. They would form a linear pair if you did that. Resulted is what we just did. We combined multiple vectors into a movement that represents their overall movement from their starting point, okay? And so when you have resultants, especially in word problems, you have to pay attention to the direction, and especially if you go back to these descriptions, quadrant bearing, true bearing, unless they say to the horizontal, you're going to assume a true bearing. You're going to assume from due north around, okay? And so unless they say southeast, northwest, and they actually give you direction, if they give you degrees, you're going to assume a true bearing. The other times, so in the second one, they were talking about coordinate plane, where while we're going to do it on the coordinate plane, unless they say to the horizontal, then you don't assume a standard. okay, you assume true. Because most of these are navigation, and that's true bearing. So if you were a captain of a boat, you would do not based on coordinate plane standard, you would true bearing north from north, because that's where all of your bearing is for navigation. So they talk about translating, and I want to talk about this a little bit because there are some where we're going to slide them around the graph. But the way I actually do it is I actually do it with two separate movements, and then I do a combination of my movements, okay? So just like we did with her walking, we did a movement, a movement, a movement, and we just combined all of those. And we're going to do the same thing with this. You have to pay attention to reference angles when we do this, okay? So if they say northeast, then you're likely going to use your reference angle, not the angle they just gave you, because you're going to draw a right triangle in the first quadrant, okay? And so there's a couple things that you have to pay attention to when they start giving you directions with these word problems. But I'm going to relate it back to the coordinate plane. We're not going to do it exactly how they do it with us. But the same concept is true. Instead of creating a triangle that's not necessarily a right triangle, which is what they do, and using like law of cosines, which is the crazy big formula, we're going to do everything in right triangle and just use SOHCAHTOA. All right? I just find it easier. All right. In her very odd competition, Tia walks north 50 degrees east, so northeast 50 degrees for 120 feet, then walks 80 feet due east. How far and at what quadrant bearing is Tia from her starting position? So how far is going to be the actual distance of how far she's walked if we were to draw a line across, think hypotenuse. And then the bearing is going to be her degrees. Now remember, we are going to have to go back to degrees from north, a true bearing, all right? So let's look at these, what's going on here. She did 50 degrees northeast. So when they say 50 degrees northeast, what they are telling me here is they are telling me that from due north, let me change colors, she is 50 degrees. All right, so she's 50 degrees from due north. So that means this right here is 50 degrees, okay? 50 degrees. 120 feet. What they're telling me when they give that number to me is they are telling me the length of this guy right here. 120 feet, okay? So I know the bearing and the length of this vector, okay? What I need to know is the composite form of this vector. So I need to know the x movement and the y movement of this vector. All right. And so in order to do that, I'm going to draw a right triangle. And because I want to keep it in where it's at, meaning my x represents my cosine and my y represents my sine, I'm actually going to draw the right triangle this direction right here. So I'm going to draw this right triangle here. Okay. And when I do that, I need to use this angle. So what is that angle? If she went 50 northeast, the angle inside my triangle is what? 25. All right, so this is 40 degrees. So we're going to use 40 degrees here to find this movement. Okay, to find this particular form here, the vector form here. So I need to find my x movement, and I need to find my y movement. How do I do it? SOHCAHTOA. And so x is going to end up being, so this is how it's always going to work out. It's going to work out to be your hypotenuse times whichever one you're solving for. So if I'm solving for my x, that's going to be cosine of 40. That's going to be what my x is. And my y is going to be 120 sine of 40. It is always that because it's going to be x over hypotenuse. And so I'm going to end up multiplying by my hypotenuse. All right. And so what is my x movement here? 91.9. Yeah, that's correct. 91.9. All right. And then what is my y movement? 77.1. Okay. So now they tell us another movement that happens. Okay. And so if I do this exact thing here, but I'm going to do another I'm going to move this over. Move this over if it will let me.
So what's the 80?
We're about to do that. Okay, so we've calculated that one. And now we're going to do a separate one. And we're going to do another movement here for her 80. What direction did she go? 80? She went east. So that vector is really simple. Due east, right? For how far? 80, okay? We don't have any degrees here because it's due east, okay? So that's not going to affect anything. She went due east. So if I were to set up the vector for the first one, it would look like this, 91.9 and 77.1. The second one would look like what? 80 and 0. Everybody see that? And so if I add those two together, what am I going to get for her movement here?
171.9 plus, comma 77.1.
So that means if I were to draw that on a coordinate plane, all right, let's talk about what that would look like on a coordinate plane. If I move this over, her resultant here on a coordinate plane is going to be way over here, 171.9, up here, 77.1. She's going to be right here, okay? I have another right triangle. Does that make sense? She's moved altogether, she's moved 171.9 to the right, or positive movement x, and she's moved 77.1 up, okay? Does that make sense? Yes. So how do I find her overall distance from where she started from? Pythagorean theorem. I'm actually searching for the hypotenuse here, right? So I'm going to take the Pythagorean theorem, the square root of 171.9 squared plus 77.1 squared. What's her total distance away from where she started from? 188.4 feet. And if we round it, we'll say approximately 188 feet. Okay? I need to know her angle as well. All right? Her angle as well. So how do we're going to solve for the angle within the triangle. All right? How do I solve for that angle? Inverse which one? We have opposite and adjacent. Tangent, inverse tangent. So you do the inverse tangent of this. All right, and what do I get there? So I get 24. We're in the same degrees. So 24 point what? 2. So I found this guy right here. All right. Is that the angle I'm trying to find if I'm doing a true bearing? No, it is not. I actually need to find this angle right here. So what do I need to do with that? Subtract from 90. There we go. All right. Subtract from 90. What do you get? 65.8, and they rounded to the nearest degree of 66 degrees. And this is also going to be a northeast movement, okay? You can do that two ways. You can just say 066, and that automatically tells them 3 digits is a northeast movement. Or you can say, just like they wrote it, north 66 degrees east.
I'm just going to say that.
Talk through it. So if I want 310 degrees, this is 90, this is 180, this is 270. All right, so from 270, how much more do I have to get to 310? 310 minus 270, I'm at 40 degrees here. So this is going to be 40. All right. It will be a negative x movement for this particular one and a positive y movement for that one. All right, if I were to draw my next one.
Oh, and this is 7.
That is going to be 55 degrees, right? But that's from the north. So if I were to draw it here, which of course is going to be not correct physically, but you know, y'all can just imagine that I drew that correctly. All right, if I draw this right triangle, then I actually want this angle here. And those are going to be both positive movements, positive x movement, positive y movement. Okay. Let's walk through this. They told me that the flipper sent it 310 degrees. So I start at due north and go 310 degrees around. My reference angle is 47 inches per second. That is the magnitude of that vector. All right. I used the SOHCAHTOA. So I just did sine of 40 times 70. That gave me my y. Cosine of 40 times 70, that gave me my x. I used a negative x here because I am in second quadrant. That is a negative x movement, okay? From due north, that's negative x movement. All right, here, then it said 055. That tells me also from due north. This was 55, but I used my reference angle of 35 degrees here. So I said the sine of 35 times 4, that's my y movement. The cosine of 35 times 4, that was my x movement. Those were both positive because I'm in first quadrant there. To get my overall movement, I added these. I added my x movements. That's where I got my negative 2.1. I added my y movements. That's where I got my 6.8. Her overall velocity is going to be the distance of that vector, which is just, so I sketched that vector right here. Negative movement for x, positive movement for y. Your vector is going to be here, right? When I find that distance, I get 7.1. That's inches per second because that's the units they gave it to me in. I calculate this using inverse tangent, but you have to pay attention to what you're calculating. All I'm calculating is this little tiny angle right here. I want to know from due north, all right? From due north, well, that's 270 plus that 73, which is how I get my 343 here.
You did SOHCAHTOA right there.
We talk about this. If a vector is multiplied by a real number scalar, the scalar multiple kv has a magnitude of k times v. So if you multiply, if it has a scalar, which is what they've been using here, scale factors, you can just multiply the original length by the scalar. That's all that's telling you. All right, so let's do this one. We're going to jump over to example 5. All right, an airplane is flying with an airspeed of 310 knots on a heading of 050. If a 78 knot wind is blowing from true heading of 125 degrees, determine the speed and direction of the plane relevant to the ground. All right. So again, I do this differently than they do it. And the reason I shift this one is because of the fact that it says a true heading. Okay. So, and I'm going to explain why it does what it does. So I do this exactly the same to begin with. I'm going to do how the airplane is traveling for my first one. The airplane is traveling 050. That tells me from due north. All right. I keep doing it a little bit. So if this is 50 degrees, that means this is 40 degrees. All right. And so for that, I'm going to use that 40 degrees, and they have 310 knots. That would be the length then of my hypotenuse. All right. The next one's a little bit trickier. So let's talk about the next one here. The next one is a true heading. So 125 degrees would put me down here, right? That would put me down here. Everybody understand 125 from true north would be down there. But this is a true heading, meaning it is hitting this vector up here at that angle, okay? So what is the movement going to be on the plane if it hits it at the tip of the plane there? It's going to move it left, right? Left, correct? And up. Yes? Does that make sense? It's going to move it left and up if it's a true headwind on the top of that plane. Meaning if I were to shift this right here up, it's going to be that direction. So while it's 125 here, it's actually the direction of the vector is towards the plane, not away from the plane. Okay? So when it's like that, I need to put it in the quadrant that makes it in that direction. In this quadrant, the direction should be this way. Does that make sense? If I'm in that quadrant. So I actually need to slide this guy up so that he is facing the right direction in the right quadrant. Does that make sense? Before that, we actually need this angle. And so now you have to use what you know about vertical angles, basically. What you know about vertical angles. So what do you know about vertical angles? What do we know about them?
They are positive and negative.
They're congruent too. All right. So that means this angle that I'm looking for is going to be congruent to this extra piece right there. So if this whole thing is 125, what is the extra piece? What do we subtract from it? I've subtracted this quadrant. What's that entire quadrant? 90. So what is that? 125 minus 90 gives me a degree of 35. So I'm going to use 35. It's going to be a negative x movement and a positive y movement for that one. All right? And so now I can calculate these. For this one, my y and my x is going to be exactly the same. I am going to say sine of 40. Sine of 40 times 310. And what does that give me? Sine of 40 times 310. What is my y movement there? 199.3. And then I'm going to say cosine of 40 times 310.
I don't think we're done after that.
We're almost done.
Well,
237.5, right?
Wait, so why did we use 310? That one, we're finding the one.
So the bottom one, they told me this one was moving at 78 knots. So that's going to be 78. So to find my y movement here, I'm going to again say the sine of 78. I mean the sine of 35 rather times 78. That's a positive movement. So that one's going to be 44.7, right? And then the cosine of 35 times 78. 63.9, but which direction? Positive or negative for this quadrant?
Negative. Positive. Negative.
Whoa.
Right? In the second quadrant, your movement is left and up. So it's negative. All right? And then to find my composite form, what do I do with those two? Add them. So what happens when I add them? You should get something like this. All right? Those are both positive. So if I were to look at what happens, I'm actually back in my first quadrant, right? Those are both positive movements. So I'm going to be somewhere, here. This one's going to be 173.6. This is 244. So how do I find my overall distance then? How do I find my hypotenuse? Pythagorean theorem, all right?
So you got
So approximately 299.5 knots. That's my movement. And then how do I find my degree?
you have to do the inverse.
Inverse tangent. All right, so I'm going to do my inverse tangent of 244 divided by 173.6. All right, that does give me 54.6. However, I want it from due north. Due north. So if this is 54.6, how do I find from due north? 90 minus that, right? So you should get 35.4. You can list it like this, 035, right? Or you can say north 35.4 east. If you just do your 35.4, the assumption is a true bearing. So you could say a true bearing of 35.4 degrees. In physics, Heather's pushing the handle with a force of 450. That's your handle. Angle of 56 degrees to the ground. This shows the resolution and exerts triangular components. Finding the magnitude of the horizontal and vertical, they literally just want these two movements on those. So you just have to do SOHCAHTOA.
That's what we did in physics.
Right.